Well, good morning, everyone, and thanks for joining me. As you probably read today, I wanted to talk to you a little bit about MapleSim and about how to export your models using the functional mockup interface, which is an increasingly popular standard for wrapping a fully executable physics-based model into a container that can be used in a variety of other ways down your toolchain. So let's talk a bit about MapleSim, a little bit about automation, and then we'll go into talking a bit more about FMI. So when it comes to automation, there's a lot of different ways that digital twins and simulation can all sort of come together, and they mean different things for different people. So just to zero in on where MapleSim fits in all of this, just take a look at this production line down below. And let's imagine that there's a few different ways in which you can consider simulation amongst a big project like that. On the high level, we've got something like the plant or process level type of simulation. This is for folks who are looking to understand how to map all the discrete events in a line together. So this is sequencing, throughput, or just simply how to lay out the plant. So there are tools to get this done. For example, Emulate 3D by Rockwell Automation is one of those. Now let's zero in on just one of these machines. And this is where our tool MapleSim really starts to shine. So on the machine level digital twin, these are for folks who are interested in understanding what size motors they should have or different mechanisms at play. This is a simulation and a digital twin that's going to understand all of the different forces and torques at play for all the physics that are going on in the movement of a machine across its entire motion path. So this is less about the discrete events of passing off product from one machine to another, but this is really how are all the joints and gears and bearings and motors all going to play together to have an impact on what's going on there. So this is useful, like I said, for motor and mechanism sizing, or also if you want to know how fast something can move product through it without the physical machine itself breaking down or, say, losing grip on the product, something like that. And then further on, and this is where FMI comes into play, if you're looking to do some controller testing on how to actually get your PLCs set up for this machine, you can start to take the digital twin from this, say the one that you made in MapleSim, export it as an FMI, and then bring that into other software so you can test your control code against a really accurate physics-based model of what the machine's doing. So it's a great way to iron out a whole bunch of bugs in your PLC code before you even have to start doing physical machine commissioning. And then lastly, for some folks, when they think about simulation, they're thinking about this FEA or CFD based method, which is really more on a part to material level. They're wondering, well, how fast can I move this thing, or how much force can I apply on this part before it starts to deform or starts to break? So this is more of the detailed level where you're doing a real finite element analysis model of the actual materials and how certain materials will perform versus others. And that has a lot to say about certain requirements, which you can then feed back into, say, the machine level, and then feed that back into the plant level. So they all sort of work together, but for this presentation, we're going to talk about the machine level. Just a quick video here to help you get a sense of what we're talking about. You just saw a whole line there, and then we're zooming in on this delta bot here. And let's say we've got some questions we want to ask about it. This is now in MapleSim, that same delta bot. And what you're seeing on the left is a visual representation of moving product over. And all the plots on the right are the actual torque and speed graphs of what's going on. And we're just quickly trying to vary here different situations about, say, how fast we're moving this thing over, how much torque to apply. So this test here would say, well, let's have 10 cycles per minute. And you can see it's relatively slow, things are moving fine. Great, we'll just change that parameter. We'll dial it up to 15. So far, so good. And in MapleSim, you can start to make all these really quick adjustments and just see what happens. So we've changed it to 20, and this is the moment you see that the suction force just can't account for the forces that are being placed on the gripper at 20 cycles per minute. So in this example here, we're just running some different fault scenarios, whether it be low suction force or cutting off that force too early. And this is kind of the stuff we're doing in MapleSim. It's just trying to run a variety of different use cases, knowing that we've got the major physics mapped out in the model itself. So I spoke a bit about virtual commissioning before. Just want to briefly touch on that. This is where you take your physics-based digital twin and you start to run testing on it for your PLC. In the automation world, this is really helpful to get answers to different sorts of questions about how you're going to actually set the machine PLC code up. So this is, what should the controller gauge be? What size motor should be used? What's the great motion path that's actually going to result in maybe the most efficient use of the motors at play? All these sorts of things. And when you can actually test your PLC code off the physics-based model, you can start to get answers to these before hooking it up to an actual machine. And again, as I get into it, this is really where the FMI standard has become more and more valuable, because it's a great way to bring your MapleSim model into automation software. So digital twins, like I've sort of mentioned the term here and there, these are physics-based models that are available before your physical prototyping. And there's all sorts of digital twins as well, and some folks will actually use that term to mean, well, I've got the product already done. Let's take a whole bunch of sensor data, process that into a curve-fitted model to try to have an estimate of what this thing can do. But when we talk about digital twins here, we're talking about making a model based off the physics of what's going on before you've got the machine made, so you can have access to a lot more tools before you've got the whole thing done. So yeah, this helps you iterate on your designs, kind of like we saw in that video where you could just change your cycles per minute, your suction force, a whole bunch of things. So you can start to tweak and understand what the best design space is before you go to physical prototyping. But of course there's some challenges to it as well. You're going to need some skill set to actually create these things, but I'll go ahead and talk about that at the end of the presentation and how to best overcome that. But once you've got a model up and running, there's a lot that you can do with it. So it's something that, like any project or technology you take on, it's a little bit of work up front, but the benefits you can get out of it are quite substantial. So just a quick sense of the process of how you'd actually build something like this. So for a lot of folks, they're already going to have some sort of CAD of their project in some popular CAD software, but they don't need to have that. So maybe they just have a concept of some mechanism they're looking to build. But let's say they start from CAD. In our tool, you can just import a CAD model from all the popular CAD platforms out there. And within MapleSim, that CAD will be broken out into all of the rigid bodies that exist that aren't going to move together. You define your coordinates, and MapleSim pulls in all the masses and moments of inertia. And then MapleSim is where you start to add in your motors and gears, and you start to actually bring the model alive so that when you simulate it, it actually runs as you'd expect. And then once you define the motion, we have a motion profile generation app. Then you can start to see how your model is actually, how all the loads and the forces are at play in every fraction of a second for your entire cycle. And it's here that you can quickly do those design iterations you've seen. You can start to tweak a lot of things. And often these simulations take seconds to minutes, and that just allows you to quickly run through things. You can also just use our apps for parameter optimization, things that allow you to really just find optimal operating conditions for your machine. And then lastly here, now that you've got this multi-domain model, you've got this physics-based digital twin, there's two different things you could do here, or two different things that are often done. At the top here, we see you can start to take all those speed and torque profiles that you saw just before, and then run them against catalog of all the different motors that you're considering for purchase. And you can make sure that you're not oversizing your motor just as a way to save money, But you can also make sure that you're not undersizing it. For some customers, certain motion profiles, there can be just quick little torque spikes that can be hard to calculate beforehand. And if you can just ensure you're not going to have those events, it'll really help prevent maintenance costs down the line. Now, in the bottom line here, this is how you can start to take advantage of using FMI for virtual commissioning. So like I said, in MapleSim, what you do is when you've got your model all set up, we have an export to FMI option, and that's when you start to define the different kinds of inputs and outputs you'd like to have access to in your testing down the road. So in your automation software, you start to bring in that FMI, and you can start interacting with it and saying, great, if I'm passing it these inputs, the FMI will just spit back out the results of that. It's sort of like just the whole model contained. And it's been really useful and really growing in popularity over the years. So if any of you folks are involved in the automation industry and use popular tools, say from B&R Automation Studio or Rockwell, you'll start to see these things pop up. Now I'm just going to flip over and show you a bit of a demonstration by an applications engineer here, Blake Martin. And he's going to go through a bit of a process of importing some CAD into MapleSim, creating a quick model, and then bringing that over to actually B&R Automation Studio to give you a sense of how you can take an FMI-based model and actually work with it in automation software. So if any of you are B&R users out there, this will be definitely relevant to you. But this same general workflow can apply for other kinds of software too. Okay, so I'll pass this over to Blake here, and we'll get this started.
I'm just going to open up a fresh session of MapleSim. For anyone who might be new to MapleSim, what we have here is on the left a list of libraries that we have. This is where the various components that we have accessible to us live, and we can use to create our model, which is going to go in our canvas here in the middle. And as we add components, we will have properties that we can adjust on the right. So for example, for this rigid body, I could change the mass, the inertia, and different initial conditions. So I'm just going to really walk through the workflow that Graham was explaining. So going from importing CAD all the way to bringing this FMU into Automation Studio. So I'm just going to go into our Import CAD option. And from my desktop, I'm going to grab this slider crank step file. We do support a host of various CAD files. So typically, whatever software you might be using to create your CAD, we will support. So bring in my file, and it's going to open up the Import CAD window, which is going to show that 3D visualization. So let me just rotate this for us a little bit so that it's upright. There we go. So this is the CAD that would have been designed in, say, SolidWorks, for example. I've already gone through the effort of kind of grouping different components into parts. So I can see if I select my crank, if I actually change the visibility so that I hide everything else, I've made this my crank. So I've selected the different components to create this part based on things that are essentially lumped together, or as this crank rotates, all of these are going to be part of that dynamic. So I will bring everything back to show everything. We do have a lot of other webinars that talk about importing CAD and kind of some of the details, so I won't go and build the full CAD, but I will just give a bit of an idea of what really goes into creating this and bringing it into MapleSim. So we have this coord option, so we select it, and this allows us to define different coordinates that we might be interested in our model. So in this case, I know that I want to place a chord here because I'm going to have rotation about this axis. And I see that it's been added to the shaft. I'll give it a name that is a bit shorter, so I'll just call it A, just for the sake of this demo. And what I can do is I want to be able to connect this crank shaft to my base. So I will actually copy this by Control-C. I will then go to my frame, select the base, and I'll paste it with Control-V. And so this is going to give me essentially a connection location on my crank component as well as on my base component, where I can then define this rotational motion. I will also add one on my base. This is going to help me fix my base to the ground. So I'll double I'm going to change the name first. I'll change it to ground so I know that this is the one I want to connect to the ground. I can change the properties. In this case, I actually want to place it in the center, the bottom of this base. So when I zoom out and rotate this, we could see that I've placed this ground location just at the bottom and at the center. So ideally, I would go through and I would want to add these coordinates at for all the different components and all the different parts that I have in my CAD. But just for the sake of time, I will just import it as is. I get a message telling me that it's been imported successfully, and it gets added to my local components. So these are components that are user generated versus the ones that are built in. And I see I can drag in my frame, I can drag in my crank. I'm going to show the port name so I can see what they're called. Just flip this component just so that it lines up a little bit better. So I see I have my ground port, so I want to fix this to the ground. I want to define a rigid connection. I'm going to go to our library under multi-body, under bodies and frames, and pick my fixed frame. I just click and connect to tell it that I want to connect the ground to this fixed frame, which is just located at my origin. Between my crankshaft and my base, I want to have a rotational motion. So again, under multi-body, I'm going to go to Joints in Motion, select my revolute, which helps me define rotation about a single axis, and I'm going to connect these. Last thing I'm going to do is I'm just going to change the direction of gravity. For my CAD, I actually had Z up as my direction of gravity, so I change it so that gravity is along the Z axis. So without adding any other components, I can actually perform a simulation, and we're going to be able to, so we see it's generating the equations, it's preparing it for integration, it's going through and solving it, and then my results are going to pop up. So we see in the results viewer in MapleSim, I can see my 3D CAD, I see the crank that I brought in, as well as the base, and if I hit play, I can actually see a simulation. So in this case, we see it swings back and forth, since it starts in this initial position, and then under the influence of gravity, it just oscillates back and forth. What I could do in MapleSim is I could actually go in here for my revolute. I can actually add some damping. So I can I'll add a small amount of damping. I'll run another simulation. And this is just to kind of give the flavor of what you can do in MapleSim and what are kind of some of the options that you can play with. So now that I've added damping, we expect that instead of just oscillating back and forth, it eventually comes and rests in this position. I can redo that. And you could play with different values for the damping. You can add other effects as well. And that's kind of one of the advantages of MapleSim. And what's nice about bringing in this CAD is we get that kind of nice rotational motion, and we're going to have the effective inertia, because when we bring in our CAD, if I actually take a peek inside this component, I have these CAD components that are going to give me that visualization, as well as this rigid body. So this rigid body is taking all the information that was in my CAD for that crank shaft. It calculates what's the total mass, as well as the effective inertia about that coordinate that I defined. So this is really why we recommend, and if you have CAD available, it's always nice to bring it in. Otherwise, you have to kind of figure out what would be your effective inertia, what would be your masses. But if you've done all this design in another software, you kind of get it for free when you bring it in. So now I'm going to do a little bit of a cooking show here and just go to another session where we have a completed model for the CAD. So we see in this model, we actually have ports defined for all the different components, and they're all connected. So if I run a simulation, now we're going to have the full CAD, the full slider crank. And I've also added this component, which is a speed driver. So I've attached it to that revolute that gave me my rotational motion between the base and the crank. And so I'm going to actually be giving it a constant speed of 5 radians per second. So now we see in our simulation, our slider crank is just rotating at this constant speed. Once I have a model set up like this, I can start asking it questions like, what is the angular velocity? What is the angular acceleration? What are the torques? I can also add more dynamics into the system. But for now, we're going to kind of set it up for one of our connector tools, which is actually the ServoSoft export. So I'm going to go in my 1D mechanical, my rotational, and I want to add some sensors. I'm going to be adding sensors to this revolute where my crankshaft is. So I'm going to go to my torque sensor. I can just drag it in. I'm going to rotate it just for the sake of kind of making it a bit of a cleaner canvas where I'm building my model. I'll add an angle sensor, and I will also add a rotational speed sensor. All right, so now I can add a probe to these so I can see the values. So I click this little crosshair, click here. I'll just call this torque, give it the units of Newton meters. I'll also add a probe here, just call it angle, radians, and I'll add a final one. This will just be my angular velocity. This will be in radians per second. What's nice in MapleSim is when you add these probes, when you run the simulation and you see that 3D view, you'll also see graphs showing the results of these probes versus time. So this is kind of a nice, quick, easy way of seeing results very quickly. Should make this big so that everyone can see. There we go. So now I can see as my simulation is running, I can see my angle is just increasing because my system is just rotating. My angular velocity is just 5 radians per second because I've enforced that. I've given that as a constant. And then I can see how my torque varies for this desired speed. The one we want to highlight is the FMU generation. So I want to set up this system so that it's ready to be exported as an FMU. So what I will actually do is I will just select everything. I'm going to create a subsystem. I'll call it slider crank. I'll go inside. And so what I'm doing now is I'm just defining my inputs and outputs. So I'll give this a name just so that it'll be a bit easier to find once I am in Automation Studio. So this is my angular velocity in. This is just my angle out. I have my angular velocity out, which will always should match my my angular velocity in, but we'll just put it so that we can see it in Automation Studio. And then I will connect, and I'll measure my torque. Perfect. So now I can go to my Automation Studio FMU generation. Double click, and once again, from here, this is just helping me select which system or which subsystem I want to create an FMU of. So I will select my slider crank. I see it updates the display. This is the one that I want. I'm going to hit load. Again, now the app is making that connection, reading my model, getting the information, and it's going to help me kind of see what's available to me in terms of generating the FMU. So I can go through here. I see as my inputs I have 1, which is my angular velocity in. For my outputs, I have my angular velocity out, the angle, and the torque, the 3 ports that I define. For my parameters, I have this K sub D, which I've used to define some damping in the revolute joints. So I've added a bit of damping. And what I want to do is, I could leave this fixed, but then I wouldn't have access to it in Automation Studio. And maybe I want to be able to change it at some point as I'm running, testing my code or just trying to test some worst case scenarios. So I will change this to tunable. And then I'll go to export options. In this case, my default solver options are fine for me. However, I do have options, and I do have fixed step as well as variable step. Advanced FMU settings for anyone who might need them or might know how to change these to really get the performance that they want. And by default, I do have this export geometric shapes and primitives. So this geometric shapes, that's going to give me the CAD that I've imported into the system. So of course, I want to see that in Automation Studio because that would be a great tool. Sometimes just being able to see your system running kind of gives you a bit of intuition as to if it's working well or underperforming, for example. So I'm just going to select my desktop again for my target directory for the FMU, and I'll just call this SC. I'll hit generate. So now what the app is doing is it's going through, it's taking all the information I've given to it, and it's actually getting all the source files that I need to create this FMU. So depending on the size of your model, this could be a bit quicker, a bit shorter. What it's doing behind the scenes is it's really creating some C code that can then be imported into Automation Studio. And in that process, we do try to optimize the code so that it does run as fast as possible. So I see that it's ready. So what I'll do is I'm just going to go, I see it's placed it on my desktop. Now what I want to do is I want to bring this into Automation Studio. So I actually have a virtual machine set up so that I can have access to Automation Studio. What I'm going to do first is I'm just going to bring over this FMU. So I can just drag and drop it onto my virtual machine. I'll make this full screen for us. So I already have Automation Studio open, and I'm just going to create a new project. So new project, again I'll just call it SC for slider crank. I'm just going to keep the default option for the configuration. And for my hardware, I'm just going to pick a standard PC. So now Automation Studio is just going to set up that new project for me, getting everything ready. There we go. Always takes a little bit of time to get the new project set up. So now what I want to do is I want to add a library that's an FMU library. So I'll click here. Just filter some of the options for me. I'm just going to double click on FMU lib. Seem to have just updated on me, that's fine. Alright, so just click here again. There we go. Now I can select my FMU. So this is the one that I just brought in my temp folder. I don't need a sample program. I'll create one myself. I'll hit finish, and Automation Studio is going to bring in that FMU file. It's going to take all of the source files, place them where it needs it, and it's also going to bring in the visualization for Scene Viewer. So we see that it's been added. I can actually expand this. This is the library it's brought in, and under this extra folder, so this is actually my scene. So it's not going to be anything exciting right now because it's not running. So let's set up a program. Let's actually get this running first, and then we'll go into Scene Viewer to see it in action. And just before I forget, I'm actually going to just update some of my system properties. This is just so that the communication between the FMU I generated and the system and how it's running are going to sync up nicely. So this time that I'm using is actually just the communication step size that I would have defined in the B&R FMU generation tool from MapleSim, and this is the task class time. So with this set up, I'll save these configurations, close these tabs. Now what I want to do is I actually want to create a program so that I can execute this FMU and kind of see some results. So I'm just going to go here. I'm actually going to create a ladder program. So I double click, give this a more interesting name. So slider crank program. I expand it. I see it's already created some of these files for me in the ladder format. So I'm going to open up the cyclic. The cyclic is the one that's going to be running continuously versus the initial and the exit. So once I'm here, and also the same kind of flow and idea would work if you're creating this in, say, a C program or in structured text. What I want to do is I want to insert a function. So I click this button, and I can search for my SC. So this is my slider crank. So you see that this is what was brought in from my FMU. So I click that, just give the name SC_0. And what I want to do is, actually I don't need these options here. Kind of clean it up a bit. I'm just going to add some space. I want to also add the visualization here. So again, I go to SC. I'll add the SC view. Now what I want to do, the only connection I really need to make is to connect the inst ref here. There we go. Again, I don't need this en. And now what I want to do is in this program, I just want to set my my slider crank FMU, I just want it to be enabled, so I'll set that to true. My angular velocity in, I'll set this, won't use 5 again, so we'll use 7.5. This KD, again, that was the damping. I won't set a fixed value just so then we can kind of show how you can update this in essentially real time and see how it affects the torque that you're going to get out. And then for the view, I also want to enable that. So I haven't defined yet these names, so it shows me as undefined. So I have to go to my variables and just kind of define them here. So using the same names from the program, what I can do is under the category, I can pick function blocks. Again, just search for the SC. And now I'm telling it that that variable is of type SC. And I'll do the same thing for the view. There we go. So I'll save that. Now if I go back to my ladder program, I see it's actually updated the type for me. So I'll also save my ladder diagram. And now what I can do is I can actually build this project. So I'm just going to do an offline installation. And so what it's going to do is it's going to take all the files, my program, it's actually going to, excuse me, it's going to compile everything and kind of do all the linking so that it can then run in Automation Studio. So it gives you some information of what's going on. We'll give you any warnings or errors. For those who are attending this, this might be a bit of a more familiar program than say MapleSim. So hopefully what you're seeing here and the way that it's built is quite familiar and is making a lot of sense. And you can kind of see that once I bring in this slider crank kind of FMU component, that you can really just, you can add control to it, you can design some logic, you can really take it as far as you normally would any other project. So I'll just create this local install folder. Close that. And now what I can do is I can open up a watch, and this is going to help me see what's going on with my program. So I'll add some variables. I'm interested in this SC knot. So I'll look at my angular velocity in and out, the angle out, torque out, and also this damping value. So we can see that it's going to run with this 7.5 radians per second angular velocity in. My damping is currently set to 0, and we can see our torque is quite small because there's no resistance. So what I can do is I can actually increase this, and we can see the value of the torque jumping up. And I can increase the damping further, make it quite high, and we see that the torque is increasing even further. So it's kind of a nice way to be able to change things kind of on the fly and see how it's going to affect your system. And again, you can add additional ports in your FMU, so any quantity that might be of interest, maybe it's some kind of position or multiple torques, multiple angular velocities. These are all things that you can have as data coming out of your FMU. And then finally, maybe we want to see this in action. So on our scene viewer file from our FMU folder, we double click, zoom in a little bit, try to get the lighting a bit better here. I will start the PVI. I'm in trial mode, so just give me this warning. And then we can see it in action. So we see we've gone from bringing in our CAD into MapleSim, creating a model that makes sense or is of interest to us, has the dynamics that we care about, generating an FMU, and then bringing it into Automation Studio, having some parameters that are tunable, having inputs and outputs, and also being able to see this 3D visualization.
Okay, well, thanks for doing that, Blake. And that should hopefully give you a sense of how you might start off with your CAD and then how you can move from that into MapleSim, set up a physics-based model, start to add the different phenomena that are of interest to you, and then show you how using FMI and using a functional mockup unit as the container to ship your model out of MapleSim, how that just creates a really convenient way for you to import this fully functional model into other programs like Automation Studio. So like I was saying right at the beginning of this though, if this is something that is of interest to you, we know that, especially in the automation world, there's many folks that see the value in this, but know that internally it's not really a skill set that they can easily find within their company. So here at MapleSoft, we've got a variety of application engineers that have different domain expertise, and we can help you with all different sorts of the aspects of the process for creating and using digital twins and virtual commissioning. And that'll range from everything from creating the digital twin to building custom-built apps that are optimized for the kind of projects you want. Let's say you just need some simple component sizing for a certain kind of design. We can make that workflow simple for you. So there's all different things we can help you with. We also offer training as well. So certainly if it's something that you're looking to just get a sense of how it could work for you, really to try and get ahead in these technologies, this is something that we have expertise in. So at that point, I'll thank you for joining me, and I will pass the presentation back to Rochelle, and happy to take any questions if you folks have them.
Okay, in order to ask Graham questions, you'll need to open the Q&A window. That Q&A window is on the bottom of your screen on that black Zoom toolbar. So we'll give it a couple minutes for questions to come in, and then Graham will start answering them. Okay, it doesn't look like we have any questions at this time, so we are really happy you attended today's webinar. If you have any additional questions about today's webinar, please feel free to email them to webinars@maplesoft.com. Thanks again for joining us. We hope you enjoyed it, and we hope to see you again soon.